All right, welcome to the last topic of the quarter. It's path analysis. I hope you can hear me and everything is recording now. The red dot is present. So let's do path analysis. I just realized that I should have discussed path analysis first before structural equation modeling, but I think it's okay. It's just more pedagogically correct if I should have talk about path analysis, because path analysis was one of the components of structural equation modeling. So I will do that adjustment next time. But meanwhile, please accept my apologies that I did not put path analysis first. It's pedagogically incorrect. I have to accept that. So anyway, let's go to path analysis and what's an overview of path analysis. Path analysis, these are our aims that we should be able to state the three conditions necessary for causality, which we already covered in structural equation modeling. We said that there has to be observable, measurement. And then that number two, there should be temporal ordering. And then that the number three was trying to remember the third causality. So temporal ordering, measurement, and that there's no spuriousness, and that it's that there are no confounding variables that we missed, and that leads to a spurious or a fake result. So that's what the three conditions of causality. And that one of the aims of this path analysis is for us to identify and the independent variables that we theorize to have indirect in addition to direct effects. So this is where the rubber hits the road, so to speak, is what to say. This is where the real work of path analysis is all about, is when we look at the mathematics behind indirect effects as well as direct effects of the independent variable that are theorized. So it's very important in path analysis that we have a profound understanding of the relationship of these independent variables in order for us to really identify these indirect effects as well as direct effects of the independent variables, which could be 2, 3, 4 independent variables, to a dependent variable, only one. So that is what this path analysis is all about. It is moving beyond doing simple regression analysis. It looks at the different relationship of 2 or 3 independent variables, and then the independent variable could have its own confounding variable, and then we look at those possible indirect variables accounting to the independent variable that will lead to the dependent variable. So what path analysis is trying to do is to demonstrate to us that this is a model of a cause and effect with a recursive path. And when we say recursive path, it really means it's one direction. What it means is that if you already if you have theorized that the path of the independent variable is from A to B to C, and then your dependent variable is D, if the path is A, B, C, D, you cannot put a variable E and then connect your dependent variable, which is the D, to the E. It cannot be that way. So it is a recursive path model. It has to have one direction. It examines the relationship in terms of direct and indirect effects of 2 or 3 or 4 independent variable to a dependent variable with only one direction. It cannot be circular, which means non-recursive. It's actually, I look at the dictionary again and said, okay, what does recursive means? Recursive is circular, but what it says in the path analysis that this is a recursive path model because it cannot be circular. And that's why it's called a recursive path model. So in my mind, the way how I simplify this is literally what it's telling us is that once you already created your theorized path of the cause and effect, you cannot put another variable on the dependent variable to have a relationship, because that becomes circular. You're going back in circle again, because it has to be that the dependent variable is the end of the model. It has to be the terminal. It is what we call the final destination. So the dependent variable has to be the final destination. You cannot say that your independent variable A, B, and C leads to dependent variable D, and then you create another variable E. It cannot be that way. In path analysis, the dependent variable is the end of the cause and effect. It is the effect. The dependent variable is the effect, and that's it. It cannot be circular. And that's why it's called a recursive path model. So that's the overview of path analysis. It answers questions regarding relationship between set of independent variables. So in simple regression, we only have one independent variable that leads to dependent variables. So we have x1 leading to y. But in path analysis, you can have x1, x2, x3. You can have 3 independent variables. And then these 3 independent variables are actually being examined for direct and indirect effect using correlation coefficients. And the correlation coefficients is something that you're very familiar, because even in our exploratory factor analysis, the first output of EFAs are the correlation coefficients, and it actually uses correlation coefficients to create or decides how many factors there are based on the strength of the correlation coefficients. So there's consistency here of mathematical underpinnings that correlations are very important values, and that they are being used to examine direct and indirect effects of the independent variable to the dependent variable. As I mentioned earlier, the most important concept in path analysis is that this is a one-way traffic. You can't go back. Once you say your dependent variable is, for example, You can have independent variable in the textbook, education, and then the other independent variable is belief, and then the dependent variable is exercise. Then exercise is the effect. That's it. That is the direction of your theorized path of cause and effect. You cannot add, after exercise, you're going to add another variable. For example, what could be other things? Socioeconomic status. Then it violates the recursive path. So when you do a path analysis, you need to really have a profound understanding already of the independent variables. You theorize your independent variables. You examine the direct and indirect effect of that theorized independent variable that leads to the dependent variable. And after you have reached in your path analysis the dependent variable, you cannot add anything anymore. That's the end of the road. And that's what it means by recursive path model. Because when you look at the dictionary and you ask yourself, what is the meaning of recursive? It actually means circular. So it's quite ironic that they called path analysis as a recursive path model, when in fact, it doesn't allow any circular path of the independent variable. So that's how I'd like you to remember what path analysis is that it's recursive, but it's quite ironic that it doesn't allow circular path analysis once you've already reached your dependent variable in your theoretical model. So path analysis is based on simple regression techniques, but it moves beyond the traditional regression analysis, because in linear regression, we just have slopes, and then we also have our intercept, and we plug that into our model, and that's our multivariate multivariate regression modeling. There's a subtle difference when you do path analysis, because it goes beyond this traditional regression analysis where it calculates slope and intercept, and then it fits into the model where you have your dependent variable and your independent variable are all adjustments of the slopes and the intercept of your independent variables, which could be 2 or 3. But here in path analysis, aside from doing slopes and intercepts, it also looked at indirect effects. So that's what makes path analysis very different than the traditional regression analysis. It's really the additive effect. It's combining direct and indirect effects of the independent variable to one dependent variable. This is a type of modeling that is considered causal modeling. So it's really cause and effect. And the path models shows theorized directional relationship among set of variables. It's a requirement before you do path analysis that the researcher will actually need to already draw the path of the different independent variables. It is what we call a priori, which means that you have to do it before you collect your data in order for path analysis to be what we call the best fit for your scientific inquiry. Because if you don't have a priori, that cannot be called path analysis. That's already going to be exploratory factor analysis. So path analysis demands, requires, prerequisite that you as the researcher must already draw the path before you even collect your data. So that is a requirement. It's what we call the a priori requirement in conducting path analysis. Right here, this is a simple illustration of what we call the direct effect. We have independent variable represented by x, x1, and you have this straight line, one direction arrow that leads to y, which is the dependent variable. And that's what we call the direct effect. It's independent variable beliefs lead to exercise, or independent variable education leads to exercise. So it's independent and it's cause and effect. But it can't be circular. You cannot say beliefs, exercise, and then you put another arrow after exercise, education. It has to be education leads to exercise, and you have a separate independent variable, beliefs leads to exercise. And that is what we call a direct effect of the independent variable to the dependent variable. But what about indirect effect? Because this is what path analysis is all about. It's beyond doing traditional regression analysis, where in our traditional regression analysis, we plug in a model fit where we calculate the slope, we calculate the intercept of all the independent variable that leads to the dependent variable. Whereas in path analysis, aside from looking at slopes and intercepts, it also looked at the indirect effects of an independent variable. So this is the additional information that we get from path analysis. It literally answers the total effect of a predictor variable, which means predictor is independent variable. So why do we say it's a total effect? Well, because it calculates both the direct and the indirect effects of the independent variable. So that is the most important questions that is being answered by path analysis. It gives you the total effect, which at the end of this slide presentation, it will show you how one variable accounts for the dependent variable using the total effect, which is already accounting both the direct and the indirect effect of that particular independent variable. So indirect effects are effects that arises indirect effects arise, or they happen, when one independent variable is theorized to influence the outcome through other intermediary or independent variables. So it's sort of like thinking that if you have independent variable A, independent variable B, and independent variable C, and independent variable A, B, and C has its own distinct cause and effect to the dependent variable D, but A and B could have an intermediary could have a collinearity, or it could be that the A and C independent variable are the one that has the influencing effect, the covariance, the collinearity, and that is being accounted for by the path analysis. And in a little bit, the slides will show you the mathematics behind the calculation of what we call the total effect, because that's what path analysis is all about. It is answering the researcher's question of what is the total effect of the independent variable leading to the dependent variable. So this is a very important concept to remember in path analysis: direct, indirect effects, and then total effects. And then it goes beyond traditional regression analysis, where it only accounts for the slopes and the intercepts of all the independent variables, but it is not accounting for the total effect of a single independent variable, which path analysis will give us. Path analysis will give us what is the total effect of an independent variable leading to the dependent variable. One example that's being mentioned here is that indirect effect would be eating a high-fat diet, which has an indirect effect on heart disease through an elevation in cholesterol level. So in general, the research questions for path analysis relate to the testing of relationships that are hypothesized. So this is a very important consideration when we do path analysis. It has to be hypothesized from the very beginning. The researcher must have a very good understanding of the state of the science of that particular inquiry, and that the researcher already theorized the possible path of these different predictor variables, how they directly and indirectly affect each other as an independent variable. And then in path analysis, the paths in the model must be supported by the data. And as I mentioned earlier, it accounts for the total effect. Mathematically, it calculates the direct plus the indirect effect of a predictor variable, which is our independent variable. And then the next one is that path analysis looks at, are there mediating effect of another variable on the dependent variable? So this goes back to the same overview of path analysis, which says it goes beyond traditional regression analysis. And you will see in a little bit that there's a lot of output here that looks very similar to the regression analysis that we have covered in the earlier weeks. Path analysis requires the same type of data, such for linear multiple regression, that it requires that the dependent variable must be a ratio type or a scale type of data, and it has to be normally distributed. So these are the assumption. The independent variable should be continuous, so none of those categorical variables, so only cholesterol, which are continuous, blood pressure, which are continuous. You cannot do age ranges. Age is okay because age is a continuous variable, but you cannot use in path analysis when you collect age data as an age range, such as you say 20 to 29 is 1, 30 to 39 is 2, and then 40 to 49 is 3. That's not a continuous independent variable for age. That is considered a categorical variable for age. So you cannot use that kind of data in path analysis. So the independent variable should also be continuous type of data. And then there should be large enough data set. The requirement for path analysis is that there should be 30 subjects per independent variable in the model. So supposing you are looking at 4 independent variables, you are looking at problem solving abilities, you're looking at self-care behavior, you're looking at patient provider relationship, and then you have this additional independent variables such as personality type, making sure that it's a continuous variable. So if you have 4 independent variable, you multiply that by 30 subjects per independent variable, you need to have at least 120 subjects to test that path analysis that you have hypothesized from the very beginning. So again, I mentioned hypothesize from the very beginning because it requires a priori inquiry. It means that you have to know what you are looking for, that you already analyze the potential relationship of this independent variable, and you already draw the path before you even started collecting the data. And that's what we call a priori. I think it could be, I'm not so sure if it's a Latin word, but a priori, it's a Priori. So here are the assumptions for path analysis. All the assumptions that apply to linear regression also applies to path analysis, such as the data has to be normally distributed, and we know how to check this. Skewness is the shortcut all the time. 0 is always normally distributed. A skewness statistics of 0 is always the perfect normally distributed data or normal distribution curve. And our tolerance for skewness is typically no more than plus or minus, whether it's a negatively skewed or positively skewed, cannot be more than 0.5. Once your skewness statistics is already 0.6 and 0.7, it really violates that assumption of normal distribution. We know what the homoscedasticity is all about. We can do Levene's test, and there are many other statistics that look at the homogeneity of the variance across the groups. And that's a requirement. That's an assumption that must be met in path analysis. And of course, linear relationship, because at the end of the day, this is general linear modeling. So we are still using one umbrella, which is GLM, general linear modeling. So in addition, there are a number of assumptions specific to path analysis. Here they are. The statistical assumptions specific to path analysis are, number 1, when 2 independent variables are correlated, and think about correlation coefficients, we always have anything that's 0.4 in our correlation coefficient. That's really already considered as a significant correlation. So I just want you to have sort of like a framework to when you think about correlations. And so correlation coefficients, when we look at exploratory factor analysis, we always have to think that, oh boy, every time we see zero point 0.4 or higher, we have to think that there is linear and the strength and direction of relationship is there. And so think about correlation coefficient and just imagine 0.4 all the time as something, as a point of reference. And then in path analysis, when two independent variables are correlated with one another and diagram as having no other variables influencing them. So in my, I just briefly mentioned that if you have beliefs as independent variable, you have education as independent variable. So belief has a straight line to exercise. Education has a straight, direct line arrow to exercise. That is what you call path analysis. It really influence and it assumed that the magnitude of this relationship is represented by that correlation coefficient. The second statistical assumption of the path analysis is that the flow of causation in the model is unidirectional. So as I mentioned earlier, it's recursive, which is quite ironic because the meaning of recursive is circular, but actually it doesn't allow circular. The model is called a recursive model, but the description of how recursive modeling is defined by path analysis is that when we move our fingers along the straight lines in the direction of the arrows from one variable to the next, we will not come back to the independent variable we started with. We will not find ourselves moving in a circle, which means that if you say education leads to exercise, beliefs leads to exercise, you cannot put another variable that will go back to one of the independent variable, which is the beliefs or the education. It cannot be recursive. It cannot be circular. But they actually call this model as a recursive model, which is quite ironic. All right. So moving on. It is assumed that the variables in the model are measured in the interval scale, so continuous, and that interval, which it means that the distance between the values are exactly the same. When we say 1 to 2, 2 to 3, 3 to 4, we know that the distance between 1 and 2 is 1, the distance between 2 and 3 is 1, and the distance between 3 and 4 is 1. So that's the minimum level of measurement for path analysis, that it has to be at the interval scale. It cannot be ordinal. There's a lot of controversies about this, lots of discussions in the academic world, because when we measure our, what we call latent variables, guess what is the usual way we measure our latent variable? It's Likert type scale. And Likert scale is actually ordinal. It's not an interval. So, there's a lot of academic discussion about plugging in our latent variables into the path analysis, when in fact, when we measure some of our psychological latent variables, in theory, they are not in interval type of data. We all know that. We all know that when we measure our psychological variables, we know that the distance between the value of 0 to 5 and 0 to 1, 1 to 2, and 2 to 3, 3 to 4, and then 4 to 5, when we ask our respondents in a Likert scale, we know that the distances between those values are not exactly the same. So just giving you a heads up that that's still very controversial here in the United States. There's a lot of statisticians who really frown upon plugging in Likert type data, or data that are obtained from the Likert type scale, and then plugging them into path analysis, because path analysis says it has to be at the interval level of measurement. The next assumption is number 4. All variables in the model are measured without error. So measurement error is assumed to be 0. And this last assumption underscores the importance of having reliable measures of variables in the path model. Now, think about this. What is it that would make us really, really meet this variable? This is basically telling us that it has to be biological markers. And so that's where there's a lot of controversy about using path analysis in social sciences and in nursing sciences, because our measures are not at the interval scale. Our measures does not have a measurement error that's assumed to be 0. But did it stop social scientists from using the values from the Likert type scale into path analysis? No, because the social scientists argue that it is the best measurement we could ever have, and that these measures have strong reliability, validity, in that these measures are based on theory, and that measures are based on theory. So there's that, just like my scale, I developed my scale 100% from theory, and it's the best tool to measure the construct. So that's where this whole argument about using psychological variables into the path analysis, because the assumption of path analysis is that it's measurement error. But the counter arguments of social scientists is that our measurement is the best measurement we could ever have, and that science will always grow and expand incrementally, and that we should never be paralyzed by the limitations of our measurement tool, but rather we will always improve upon the existing measure and continue to overcome this handicap, these limitations that we have in measuring the psychological variables. So I'm with that camp. I really believe that eventually, when we get into what we call physics level kind of science, where it's exactly, perfectly, mathematically error-free, we will get there. But for now, social science, nursing science, we are still refining our tools, our measures of scoring, getting values of psychological variables. But we will get there. That's why our Cronbach's alpha is set at 0.7 or higher. That tells you already that there's already measurement error, because we don't have a Cronbach alpha that's 1 that perfectly accounts for the true measurement and internal consistency of measuring the construct that you want to measure all the time. Unlike in physics and chemistry and other biological sciences, where it's already perfectly mathematically exact. So